last talk of this session, and the speaker is here, so the floor is yours, please.
Thank you. First of all, I would like to thank the organizers of the conference for inviting me. And this is my joint work with Alexey Marian, who is with Novosibirsk State University. The brief outline of my talk is as follows. I start with basic definitions. Then I give some history on previous and related results, and finish with main results. By F to the n, I denote the n-dimensional vector space over the field of two elements. The code, a binary code of length n is a subset of vectors from F to the n. A code is called linear if it is a linear subspace. For a pair of vectors of the same length, one might define the Hamming distance between these two vectors as the number of distinct symbols in vectors x and y. The Hamming weight of the vector is the number of non-zero symbols of this vector. And the minimum distance of a general code, which can be nonlinear, is defined as the minimum of the Hamming distances between pairs of distinct code words of the code. In case when we speak of linear codes, the minimum distance is actually the minimum non-zero weight of the code words. We are especially interested in certain type of linear codes that could be defined using parity check equations involving inclusion matrix. So we use the same matrix that was used in one of the previous talks. For T and K, for T and K, such that T is greater than 0, less than K, and K is less than N, we denote by WTKN the inclusion matrix. Its rows are indexed by T subsets of an element set, which are integers from 1 to n throughout the talk, and the columns are indexed by K subsets of the n element set. And the UV element of the inclusion matrix is 1 if U is a subset of V. And this element is 0 otherwise. One might consider a binary linear code, which is a solution space of the system of linear equations with the matrix of the system being the inclusion matrix. So this system we consider over the binary field. And the main problem of the talk is what is the minimum distance of the code CTKN. So I move on to describing previous and related results. Actually, this will be quite a large section. I give a mini outline of this section. I start with some general lower and upper bounds on the minimum distance of these codes. Then I speak about an infinite and a soft infinite series for codes C, K minus 1, K, and we know their minimum distances. Then I speak about the dimension of these codes, generalizations, and connections to designs of certain type. So lower and upper bounds on the minimum distances of the codes are as follows. A lower bound could be obtained from using the notion of a derived design. We'll speak about this notion maybe later. But according to this approach, the minimum distance of the code CTKN is at least the minimum distance of the code C with parameters t-1, k-1, and n-1 plus 1. And in particular, the minimum distance of the code CTKN is greater or equal to t plus 2. This approach for bounding the minimum distances was mentioned in the work of Potapov, and the upper bound on the minimum distance of the code is actually 2 to the power t plus 1. So we have this very large gap between the lower bound t plus 2 and upper bound 2 to the power t plus 1. Now I'm going to speak about one solved case when t is k minus 1. The minimum distances of the code c k minus 1 k n is k plus 1 for all k and n. And this was shown in two works that use different terms, and actually in the first of them, the application of these codes for from the positions of locally recoverable codes is used. These codes are used in storage systems. I'm not going to give more details on this one. Just want to emphasize the fact that these codes could be interesting from various points of view, even in coding theory. I move on to another important parameter of the code, which is the dimension of the code. Once we know the rank of the matrix, the inclusion matrix over the field of two elements, we know the dimension of the solution space. We know the dimension of our code CTKN by its definition. And finding the ranks of these inclusion matrices is a well-known combinatorial problem that was intensively studied. I give just two of many references here, work by Wilson and Lineal and Rothschild. In the work of Wilson, a solution is given for over any field, and over the binary field, the solution is given for over by Lineal and Rothschild. Lineal and Rothschild gave the solution for binary field. So now I will speak of a generalization of these codes. In an ordinary definition of subset inclusion matrix, we have a matrix whose rows and columns are indexed by subsets of certain size, and we got one entry being equal to 1 if a certain subset is a subset of a larger subset. In the following generalization, one might replace the word subset with subspace. And now we consider a matrix with rows indexed by t subspaces and columns indexed by k subspaces. And those are just subspaces of n-dimensional vector space Fn. And in the same manner, we define the inclusion matrix. Its UV element is 1 if U is a subspace of V and 0 otherwise. And also in the same manner, we can define our code, the new one, to be the solution space of the system of linear equations with this subspace inclusion matrix. And these codes are interesting from various points of view. In particular, they are used in constructions of low density parity check codes. I refer to work of Cao, Lin, and Fusarier that has over 1,500 citations. For further generalizations of these codes and their properties, including minimum distances, I refer to works of Lavrov, Storme, and van der Voorde, and also work by Krotov. So several connection to design. I remind you the definition of ordinary design. T and K lambda design is a collection of K subsets of integers from 1 to n, such that any T subset is in lambda blocks. The following definition was suggested by Wilson. A Peary T and K design is also a collection of K subsets, but now we require that any T subset is contained in 0 via modulo P blocks. So lambda now is not always a constant, but it's a constant by modulo P, which is 0. Actually, we can see that the code words of our code CTKN are actually the same as Tuori T and K designs. For a code word, one might consider its subword, which is the set of indices of non-zero positions. The positions of a code word are actually K subsets. Now, since the parity check equations should be fulfilled for our code word, the support over a code word is a collection of subsets such that any T subset is an even number of blocks. And the weight of the code word is coincides with the number of blocks in design. So our code CTKN is the space of Tuori T and K designs, but we have some bad news about this Tuori designs. We have no Fisher inequality, and also some other properties for designs fail to be true for them. For example, not any T design is T-1 design here. For example, one can take an ordinary design, 2742 design, known as Hadamard design, which is unique up to isomorphism. And if we look at it as a Tuori design, it is a Tuori 274 design, because any two subset is contained in 2 blocks. 2 by modulo 2 is 0. This implies that we have a code word of our code C2 for n of weight 7 for all n equal for n at least 7. Weight 7 here follows from the number of blocks in our Hadamard design. So I move on to describing main results of my talk. I give a construction for Tuori 2 and K designs with 7 blocks for all K congruent to 0 via modulo 4. we start with 2742 Adamar design, and then we increase 4 to K. For any block B in design D, in the Hadamard design D, we set a new block, which is I plus 7 multiplied by S, where S runs through values from 0 to n divided by 7 minus 1. So I here should be here. Sorry. And actually, if we look at this definition of new block, we take all these blocks for blocks in D. The collection of such blocks is a 2-array 27K divided by 4K design for all K congruent to 0 modulo 4. It has 7 blocks, the same number of blocks as Hadamard design. Actually, very simple construction here, but still it gives a slight improvement of the minimum distance. As it shows that there are code words of weight 7. Now we take a design that we have just constructed. For some reason, it is denoted by D here. And from this design, we construct a 2-array T and K design for T at least 3. So we increase 2 to T here. This design will have 7 times 2T plus 2 to the power T plus 1 divided by 8 blocks. So I give a particular case of a construction, actually, for T equal to 3, but also several generalization could be made. So we start with the design that we have just constructed. And for any block, we set 2 blocks, 2 new blocks. Block with 1 element, 1 new element, and a block with the second new element. So the number of blocks is increased by 2, is increased by the factor of 2. And also we increase this way T to, for example, in our case, this is 3. So we obtain a 3n plus 2 k plus 1 design. Here, and also in this construction, we can vary the initial design. It could be not always a Hadamard design. Some other generalizations would be also made here. We can obtain the following improvement of the upper bound for any T and some K. The upper bound, the general upper bound is 2 to the power T plus 1. And we improve it to 7 multiplied by 2 to the power T plus 1 divided by 8 for all K, such that K minus T is 2 via modulo 4. We also give a complete solution for case when T is equal to 1 or 2. The minimum distances of the code C1KN is 4 for odd K, and it is 3 for even K. These is asymptotically on n. And the solution for the case when t is 2 is as follows. Let d be the minimum distance of the code C to Kn. Then the minimum distance is 4 if K is 3. In all other cases, it is greater than 4. It is 6 for odd K, 7 for all K divisible by 4, and minimum distance is 8 when K is divisible by 2 but not by 4. And also, once we obtain the minimum distances of the code C2Kn, we can also improve the lower bound on the minimum distances of the code CTKn for t at least 3. And we show that minimum distance is at least t plus 4. I remind you that the previous lower bound is t plus 2. Very slight improvement here so far. So the future work is as follows. So we would like to find the minimum distances of the code C3Kn. And the lower bound is 7. This is what we have so far. The upper bound is 16, and it also could be improved to 12 or 14, depending on the value of K. So we have some work to be done here, but still we are pretty much optimistic. I give the conclusion. We studied the minimum distances of the codes from inclusion matrix. We found the exact values for the minimum distances of these codes for t equal to 1 and 2. We gave an improvements on the upper bound in some cases and lower bounds on the minimum distance also. Thank you.
Thank you very much for your interesting talk. Are there any questions to Ivan?
Excuse me, I have a question. So
Yeah,
how
please.
about the, sorry? How about the carving radius of the codes you studied?
Actually, a very good and interesting question. Can't say anything so far, but it is a good question. I don't know anything about it so far. Thank you.
Thank you very much.
Any other questions? I just wondering which approaches do you use to get new bounds you mentioned at the end of your talk.
Mm-hmm. So the lower bound it just follows from the concept of derived design. So
right, yeah, but I mean the next slide. So you showed us, yeah, these bounds. So which approaches do you plan to use or used?
So far we believe that the minimum distances are not so small to be like 7, 8, 10. We believe that actual minimum distances are closer to the upper bounds. And also the study of the codes for t equal to 2 shows that actually the minimum distances are pretty much close to the upper bound, which is 8.
Right.
And here we believe that it will be close to 12, 14, or 16, depending on K. As far as approaches, we believe that the integer linear programming should work for this case because,
really?
Yes, from theoretical point of view, actually we have reached quite a limit in my opinion. So I suggest that we try some linear programming approach here. So using computer, maybe.
I see. I see. Okay, thank you. Any other questions?
Thank you for the question.
Yeah, if not, then let us thank Ivan again. Thank you very much for your talk. It was very interesting. Some new ideas and some new challenging future for you, right? Yeah. So, yeah, low bounds, upper bounds. Yeah, it would be interesting to see these results. Well, 12 or 14, or do you think 10? Is it possible to get 10? Why not?
Maybe, yeah.
Yeah, okay, we will see. Okay, thank you very much. Well, it was the last talk of our today's session.